This first video is going to be an introduction to calculus. So calculus came from two problems, the tangent problem and the area problem. So tangent gives rise to a concept in calculus called derivatives. And the area problem gives rise to a concept in calculus called integral. And finally, the big shebang is a theorem called the fundamental theorem of calculus, which says that these two things are not only related, but they are inverses of each other, in a sense like times is the inverse of divide. One operation undoes the other. So what then is a tangent problem? Well, first of all, what is a tangent? So let's give a definition. So tangent line to a curve is a line that intersects a curve at one point. So let's say we have a curve, and we'll call this g of x. And we have a line, and we'll call this f of x. Then it will intersect at xy. So is this a tangent line? Well, in principle, let's say we have a parabola, and we'll call this y equals x squared. Let's say this is the point 0, 0. So let's look at this point. I think we could all agree that y equals 0 is tangent to the curve, right? So this is a perfectly good function, a constant function. It doesn't end anywhere, and it's defined over the entire real line. So let's remember a formula. So what is this formula? Well, it's a quotient of two quantities. It's a formula for a slope of a secant line. So what is a secant? Well, secant is any line that intersects a curve at two places or 2 points. So a tangent line is a special kind of secant line. So the slope of a secant line to a curve given some function f of x through points a, b is rise over run. So we can say that f of b minus f of a all over b minus a. So if we let a equals x and b equals x plus h, then we get the formula f of x plus h minus f of x all over h, right? So these are really two ways of describing the same thing, which in picture form looks something like this. So if we look at this curve and we draw this triangle, we know that this side has length b minus a, and this side has side length f of b minus f of a. And we know that the slope of a triangle equals rise over run, which is just this formula, right? So how then is a tangent a special kind of secant? So here's a question. What is special about a tangent? So what happens when we take this drawing? Let's make it specific. So let's say that a is 1 and f of x will be x squared, and let's make b 2. So let's make a little chart. So we'll start off with b equals 2. So f of a is 1, which is 1 squared. So that's going to be 1. And what's f of b? So f of b is 2, but we have to square that, so that's going to be a 4. So the slope, so f of b is 4, minus, and then f of a is 1. All over b, so b is 2, minus a, which a is 1. So that's going to be 3 over 1, which of course would just be 3. What about when b is 3 halves? So now I'm going to move a little closer. So f of a is still 1, but now f of b is 3 halves, and if you square that, you're going to get 9/4. And then the slope, if you plug it in this formula, you're going to get 5 halves. But instead of 5 halves, what is that in decimal point? So it's going to be 2.5. And if I were going to continue to do this, get even closer, let's say 1.25, 1.1, you'd find that these slopes are getting closer and closer to a number. And that number is the slope of a tangent line, which in this case is 2. So as b gets close to basically 1, but b can't be 1, right? Because if they're both 1, then b minus a is 0, and we're dividing by 0, so it breaks, right? So in order to address this issue, well, that's the entry point of calculus. So to sum up then, what is special about a tangent line? Well, the tangent line is sort of what happens at the very bottom of this infinite list, right? So as one of the secant points gets closer and closer to the other, the line gets closer and closer, which will eventually be a tangent line. So back in the day, people that thought about math thought about this, and people that thought about physics thought about exactly the same problem, but they thought about it in terms of physical quantities. So the next question is, what is instantaneous velocity? And is there such a thing? So let's say I'm standing on a building and I throw a rock off the building. And I shoot it straight, horizontally, right? And let's say that the function that describes the position of the rock, f of x, is where x is now time. So this is your x-axis. And let's say that f of x, let's say my function is going to be 10 minus x squared. So the rock starts off at 10 meters. So it starts off at 10 meters and I just throw it straight out and it follows an arc and hits the ground. So this is a function that describes position. So how is velocity related to position? If I were to give units to measurement of f, like f of x is described in meters, and if I wanted to know the velocity of the rock, what would the units be? So if f of x is meters, then the velocity, so we'll call it v of x, would be meters. So meters per, and that's time, so we'll call it per seconds. And we can find the average velocity over any period of time, right? Let's say by looking at a function evaluated at 2 different times and just computing the slope of a secant line, like we saw earlier. So the average velocity over time interval a, b, well, that would be equal to the slope of a secant line through f of a, f of b, which, using our formula, so let's measure it where I first throw the rock off. Let me make a equals 0, so that's right here. So that would end up being, what's f of b? So f of b is 10 minus x squared, so that would be 10 minus b squared minus f of a. So if f of a is 0, then that would make it 10. All over b minus a, which is just b minus 0, right? Which would just be b. Which is, so if you have positive 10 and negative 10, that would be negative b squared over b. And this b crosses out with this b, so that would just be negative b. So that was the amount of distance that the rock fell over a period of time over b seconds, right? Which corresponds to all our notions of velocity. So the distance traveled per unit time. So the meters we traveled, that's this part right here, right? And the seconds that elapse, well, that's this part. And we divide them and we get the slope, and that's the velocity. But is it possible to have instantaneous velocity? Because to compute this, I had to average stuff, right? But when you drive a car and you look at the speedometer, the needle moves back and forth continuously, right? So it's like a function of time in its own right. So people interested in physics wanted to come up with a function for the velocity. So let's see what happens as we average over smaller and smaller periods of time. So let's basically move b close to a. So if this is b, so we're going to move it closer and closer and closer to a. And let's take the average over fewer and fewer seconds, and that will make our secant line start to look like that, right? So this whole slope ends up being 0. It makes sense because the top of the parabola has a tangent line that's horizontal to it, right? So it seems that we can get all the idea of slope of a tangent line by starting with a secant and making one point get as close as possible to the other point. And we could take that abstract idea and put it in various physical contexts and come up with derived quantities like velocity, right? Or acceleration. Anything that depends on time.